Hello, and this is my final presentation for ISDN2603. Here's a quick review of what I'm going to talk about. First is introduction, then the design requirement, choice of material, atomic structure, and other functional properties. Let me introduce my project, HydroWing. HydroWings is about a wheelchair specifically designed to let lower body disabled people get on a kayak without another person's assistance. A disabled person would roll the wheelchair on top of the kayak, and the seat is lowered by a mechanical servo motor arm that is attached to the wheels. Just like that, it has successfully transferred the disabled person from a wheelchair into a kayak. The specific component I would like to find a material to work with is the frame of the wheelchair. The material should adhere to constraints to be suitable for the project. It should be water resistant as it would be submerged in water for prolonged periods of time during kayaking. Sand resistance as it would be used to navigate around the beach, and lightweight to make the wheelchair easier to carry around when needed and not exceed the kayak's weight limit when it is floating on the sea. Also, it should be strong to be able to support the weight of the person, with smooth texture so it will feel more pleasant to touch or lean on, and not hot to touch under prolonged exposure to sunlight, which means it has low thermal conductivity so that when the user touches the kayak, they will not be burnt. The choice of material has narrowed down to carbon fiber reinforced polymer, ZZ60, and titanium alloy, titanium 6 aluminum 4 vanadium. Titanium alloy is strong and durable. It is lightweight and resistant to different conditions. However, it is expensive. Carbon fiber reinforced polymer is ultra lightweight. It is strong and resistant to different conditions like heat, chemicals, and most importantly, seawater. However, it is extremely expensive. I researched more on the statistics after the midterm presentation, comparing their mechanical properties. Sensitivity shows that CFRP is lighter than titanium alloy, while Young's modulus described the tensile elasticity, where titanium alloy wins. The yield strength can be found when doing tensile tests, and the first local maximum of the strain graph is the value. Poisson's ratio shows the tensile deformation of the material, and for our project, we want it to be as little as possible, so that the wheelchair will not deform during usage. For CFRP and titanium alloy, they have similar deformation. Moving on to the thermal properties. Their thermal conductivities can be determined which will feel hotter under exposure to heat and radiation. While both have extremely low thermal conductivity, CFRP is lower. Titanium alloy will expand more than CFRP as seen by thermal expansion. However, CFRP will enter gas transition when it reaches high temperatures of 100 degrees, which is also the maximum surface temperature. It is also unable to surface at low temperatures, only reaching negative 60 degrees. The melting point of CFRP is also low compared to titanium alloy. In terms of price, the price of titanium alloy is less expensive than CFRP. After considering different aspects, the final choice would be titanium alloy. Titanium alloy is less expensive and easier to deform and manufacture. CFRP also has another disadvantage, like limited shelf life, as the epoxy matrix will degrade and have reduced lifespan when exposed to sunlight, which is the condition for our usage. It has lower impact resistance compared to titanium alloy, which makes it bad for wheelchairs. It is also hard to repair, requiring specialized equipment, and is also a costly process. After deciding on the materials, let's take a deeper look at the properties. First being its atomic structure. At alpha phase, it adopts a hexagonal close-packed structure, and at beta phase, it adopts a body-centered cubic structure. The image on the right shows the structure of titanium 6 aluminum 4 vanadium, and this is the lactide structure of titanium 6 alloy 4 vanadium, and its phase diagram. What about other functional properties? These are the resistance factor of titanium alloy in different environments. These statistics of titanium alloy helps us understand its behavior under load. Fracture toughness describes the resistance of brittle materials to the propagation of flaws under applied stress. Bulk's modulus measures how resistant a material is to compression. Modulus of rupture is like a 3-point bend test, measuring the bond strength of the test specimen. Shear modulus is an indication of a material's rigidity and its resistance to deformation due to shear stress. Titanium 6 aluminum 4 vanadium is vulnerable to a lot of common failure modes, one being fatigue failure, as cyclic loading will lead to the initiation and propagation of cracks over time. Different heat treatment methods can lead to different physical properties. Titanium alloy is highly resistant to corrosion but suffers from stress corrosion cracking. Where is the material loss over time? Repeated thermal cycling will crack the alloy after expansion and contractions, and air oxidation is observed over the temperature range of 600 to 800 degrees. Titanium alloy has a recycle fraction of about 20% and 700 megajoules per kg of embodied energy. This is the forging process of titanium 6 aluminum 4 vanadium. This is the end. Thank you.